Good afternoon, everybody. Thanks for being here today. My name is Sean Hargreaves. I lead the Direct3D team at Microsoft. And I'm going to talk a little bit to introduce what variable rate shading is, and then hand over to some partners from Intel and Firaxis who are going to demo this running in action and show it being applied to some real game content. Variable rate shading is a new feature in D3D12, and it's the biggest change to the triangle rasterization pipeline in a really long time. I'd say probably since we first added support for multiple render targets, which is more than a decade ago now. And the reason the rasterization pipeline hasn't changed is that it's pretty good. We've had a lot of experience at rasterizing triangles, and hardware knows how to do this well. So I thought it would be interesting to start by backing up and talking a bit about why we're changing it now and what the motivation for adding something new to this is. So if you join me as we rewind in time back to the dawn of the modern 3D era, things started with hardware that did not support variable rate shading. It ran at very low resolutions. That meant the pixels were big, and there was a lot of aliasing. But they were pixels. It was real-time 3D. It was a good place to start. Wind forward, I'm going to skip past a bunch of years of all kinds of exciting innovations. And there's one particular innovation that's very relevant to variable rate shading, and this is the introduction of multi-sample anti-aliasing. The reason this is interesting is because variable rate shading builds on a number of the same kind of ideas and insights. And the key thing that made MSAA interesting was the realization that as GPUs were getting more powerful, resolutions were going up, but people wanted image quality to go up faster. And there was an interesting realization that triangle edges are way more visually important than the shading of the interior of triangles, usually for most content. So you could get an interesting efficiency if you decoupled the two and ran pixel shaders at one resolution, but then did Z-buffer tests and triangle edge anti-aliasing at a higher resolution, and that's MSAA. This actually ends up being super friendly for hardware efficiency, because the other advantage is that if you're replicating a single pixel value to more than one pixel in the frame buffer, that's incredibly compressible. And this is about the same time that hardware was starting to do tricks like bandwidth compression to save bandwidth. So MSAA plus Z stencil compression is a really good combination for performance. Zoom forward a little bit more. And there's a trend here that resolutions just keep going up every few years. We're dealing with more and more pixels, and also more advanced tricks to get better quality out of what pixels are available. So around the Xbox 360 era, a big thing that came in was display scaling. 360 games didn't have to render content at the same resolution that was output to the TV. They would usually render quite a bit lower, trading off higher quality, being able to shade fewer pixels and therefore do more math for each pixel. The output for this was typically a 720p resolution, but games would render lower. And kind of ironically, they would often actually render at a lower resolution, but using MSAA, downsample the MSAA, and then scale the image up to fill the TV resolution. And this idea is also kind of an input to the design of variable rate shading. Bringing things all the way up to today, the general theme of graphics today is that resolutions are really, really high. There's a lot of pixels. I'm kind of half joking showing this diagram going up to 8K resolution, but it's only half a joke. We can all see that 4K is a thing today, and people are talking about 8K. 8K hardware is out there. And even at 4K, that's a crazy number of pixels. I'm presenting this from a Surface Book laptop, which is just a little integrated, not a super powerful GPU, but it's rendering at 3000 by 2000 resolution. It's a lot of pixels. And this gives game developers a dilemma. Do you really want to shade every single one of those pixels? That is the correct thing to do for best clarity and resolution of content. Or do you want to shade fewer to get better perf, or maybe use more advanced shaders? And then you could, there's a whole panoply of techniques people use to achieve this. You could upscale, like the Xbox 360. People do things like dynamic resolution, where you adapt the resolution to the frames. So if a big cloud of particles goes off, you just drop the resolution down to compensate. Techniques like checkerboarding are becoming popular. But the theme of all of these is there's a lot of interest in rendering fewer pixels than actually goes to the display while still outputting a high-quality image. But there's really kind of a flaw in all of these approaches, and that is that content is not all the same in importance. Some things just matter more than others. So if you just take a one-size-fits-all solution, like deciding what resolution should the whole frame be at, you're making a suboptimal choice for different kinds of content. I live in Seattle. In Seattle, our skies are usually gray. They're extremely low frequency. Shading a northwest sky at 4K is completely pointless. It would be nice if I didn't have to do that. So picking one resolution per frame is just too coarse. even if I do the dynamic thing where, hey, there was a big explosion, loads of particles, so I dropped the res to compensate, well, that explosion might not be covering the whole screen. The right-hand side of my screen I can still see the landscape in full detail. I'd like to shade that at full detail and just drop pixel density where things are covered and don't matter as much. And checkerboarding is a valuable technique, and people are getting some good results from it. But again, it applies to the whole frame. You can't just checkerboard parts of a scene. And it also has some implications for visual quality. It implies a filmic type of temporal post-process, which works really well for some things, but not as well for other things, depending what visual style you're really aiming for. You can start doing things like a different resolution per layer. A lot of games will compose things out of pieces and change the resolution accordingly. So maybe you draw your 3D scene at one resolution and then particles at a much lower resolution. It's generally hard to get the intersections right when you do this, and we've all seen those games where the particles look great until they go through a piece of scenery, and then you've got huge stepping artifacts. There are ways to fix those, but they're not ideal. So we think all of these solutions are really just kind of not as good as it could be, and that's why we are introducing variable rate shading. So the idea here is to build on what worked in MSAA, particularly the realization that triangle edges and depth stencils should always stay at full resolution, but you can drop the shading rate for pixel processing. But instead of just doing that globally, with variable rate shading, you can do this selectively where it matters. So you can choose a different shading rate per object, per triangle, or per area of the screen. This lets you shade things where it matters and shade less where it doesn't matter. So you can maintain image quality by not dropping the detail from places where you need the detail, but you also get more performance because you're not spending time shading where you didn't need to. When I say drop the shading rate, I think a few diagrams might help to understand what that really means. So this is a pixel grid. This is a triangle that I'm drawing. With conventional triangle rasterization, I would fill those gray pixels. And to do that, I would run the pixel shader once for every one of those green dots. That boils down to 27 invocations of a pixel set shader to render that triangle. Kind of obvious, there's one pixel shader per pixel. That's how it always used to be. With variable rate shading, I can do this. This is with a 2x2 variable rate shading tile size. So each of those yellow squares is a coarse pixel. And I'm using 2x2 coarse pixels. So I'm still writing the same gray squares in the actual frame buffer, but I'm only running the pixel shader once for each yellow dot, and then the value computed by that pixel shader is replicated along each of the yellow arrows to fill the destinations. And you'll see that even if a coarse pixel goes outside the triangle, that replication doesn't happen where the frame buffer pixel was outside of the triangle. This example is using centroid sampling, so where things fall outside the triangle, I'm shading out the point that is still inside of it. You can also do variable rate shading with center sampling. It's the same, works very much like MSAA. And if you're thinking that this looks an awful lot like a diagram of just 4x MSAA using centroid sampling, you're absolutely right. It's almost the same thing. It's like MSAA just with more control over the details. And it has similar efficiency to what you're used to with MSAA. And there's obviously a perf gain from shading a triangle this way, because now I'm just running the pixel shader 11 times. That's less than once per actual pixel. The next level of control comes in when I start subdividing even within a triangle. I don't have to just shade the whole thing at 2x2. So in this diagram, I'm using a range of different coarse pixel sizes. I have a few green pixels in the top left where I'm shading at 1x1 full rate. I have a couple of 2x2s. And I also have some anisotropic shading rates where the red in the bottom left, I'm using a 1x2, and then the orange at the right, I'm using a 2x1. This is slightly more pixel shader invocations. This time it's running 14 to shade that triangle. But it's still only about half the amount of shading work as the original full shading rate. And variable rate shading gives you the control to do this kind of thing. So there's a couple of questions that come up when we introduce people to this concept. One of the first is usually, what about gradients in the pixel shader? How does MIP level selection work? And the answer there is pretty simple. It works at the coarse level. So if I reduce the shading rate to 2x2, my gradients scale accordingly, and my MIP level selection drops accordingly. That's normally what you want. If you're not shading in as much detail, you want to use a less fine MIP so as to preserve correct filtering, and you get a saving in texture bandwidth as well as pixel shading, so it's a double win. If that's not what you want, There are a few tricks if you're doing temporal anti-aliasing with variable rate shading. Maybe you actually want to force to a finer MIP level. You can just use MIP bias to compensate for the shading rate adjustment. One implication of this is that super tiny triangles and variable rate shading are not a good combination. Super tiny triangles are already not a good thing because of the quad-based nature of shading. If you draw a triangle that covers just one pixel, the hardware will still shade 4 in a 2x2 grid so that it can compute gradients. If you're using 2x2 variable rate shading, that just gets bigger. So now your triangle covers a 2x2, but the hardware actually still has to scale up and shade for 4 coarse pixels. And generally, we think this is not really a problem in practice because it's not efficient to use that many tiny triangles already. And variable rate shading is really the biggest win for very high resolution rendering, where you're going to have a higher pixel to triangle ratio. But it's something to be aware of. This is a good technique when your triangles are larger. Another common question is, how does MSAA work in this world? And yeah, the two are compatible. If you have MSAA enabled and then do variable rate shading over the top, first, the variable rate shading will replicate a single value to multiple pixels. And then MSAA will replicate that pixel value to multiple samples within it. You can end up with very high sample counts this way, but that's sometimes useful. So let's look at the code. I hope there are some programmers here. So I'm going to show what the APIs to use this look like. The high order bit here is variable rate shading is not a complicated API. It's an easy thing to integrate into existing engines. It doesn't require reworking a ton of code. You'll see there's not that much API surface here. Start with the check feature support call. Not all hardware is going to do this. This requires silicon that supports the feature. And you'll see here there are 3 options you can get back from that. Maybe it's not supported, or the hardware might be tier 1 or tier 2. Tier 1 of variable rate shading capability has just one API, RS set shading rate, and you tell it what shading rate you want. So this lets you change the rate per draw call. And this is a reasonably high frequency API. You can do this multiple times per frame to draw different objects at different shading densities. There are 4 shading rates that are guaranteed to be always available on all VRS implementations, 1x1, 1x2, 2x1, and 2x2. And then there's also an optional capability that some hardware will go further and expose 2x4, 4x2, and 4x4 shading rates. You need to check for a cat bit before using those larger values. I showed the bit patterns of these enums here, and that's actually significant because they're not just a zero-based enum. If you look at the encoding, the way these are actually defined, there are 2 bits of horizontal shading rate and 2 bits of vertical shading rate combined in log space. So 0 maps to 1, 1 maps to a 1's in both places is a 2x2 shading rate. And this means you can do math on these values if you want. You can decompose them and shift them and treat them as packed vectors rather than just enums. Some implementations will also support variable rate shading tier 2, which introduces 2 new capabilities. One of these is the ability to change the shading rate per triangle within a shader. This is done using a new HLSL intrinsic SV shading rate. You can write this from a geometry shader or a vertex shader. If you write it in the vertex shader, the value from the provoking vertex will be used for each triangle. This is also available in the pixel shader, where it's an input. You can't change this from inside a pixel shader because you've already started shading at that point. But if your shading pixel shader code wants to know what rate it's being shaded at, it can query this value. The other capability of tier 2 is to use a low-resolution screen space image to adjust the shading rate based on spatial locality. And this is done using a second API, RS set shading rate image. And you give that a texture. This maps to the render target that you're drawing to, but at lower resolution. So the texture is the render target is divided into tiles, and each tile corresponds to 1 texel from this shading rate image. It's an R8 format, 8-bit value. It has to be a UAV, cannot be a render target, but you can write to it from the GPU from a compute shader or by copying to it. Before binding a texture as this, you have to transition it to a new resource state, which is the shading rate source. And it's a pretty simple model. One thing to note here is that the tile size can vary depending on the hardware implementation. You'll see different sizes of 8x8, 16x16, or 32x32. So you do need to check that, and that will affect the granularity at which you can adjust the shading rate this way. And now that we have 3 different ways to control the shading rate, per draw call in tier 1, plus your choice of per triangle or per screen space image in tier 2. What happens if you use more than one at a time? This is done using a fixed function combiner mechanism. So this starts, we have the per draw shading rate and the per triangle shading rate. And these two values get fed into a combiner. Then we add in the image-based screen space shading rate and feed that into a second combiner. And the result of that second combiner is what is used to drive the rasterizer. The combiners are set using the API RS set shading rate. The same thing that sets the base shading rate can also take an array of these two combiner values. And there are a set of options for these. You can just pick either one of the two inputs and throw away the other using pass-through or override mode. You can take a min, or you can take a max, or you can add the two rates. The important thing to note is these min, max, and add operations are operating on the 2-bit packed format, not just on the numerical value of the enum, because that would not be terribly useful. So min is a min of the horizontal and vertical dimensions of the coarse pixel size. When you do the sum, that's operating in log2 space. So if you add a 1x1 shading rate to a 1x1 shading rate 1 is represented as 0 in log space, so the result is still 0. It's not numerical addition, it's a log space addition. But this gives you a ton of options to combine the shading rates in different ways. So you can have use any one of the mechanisms as your kind of basic selection of what shading rate is interesting, and then use one of the other sources to override that or tweak it for specific objects or where you need particular control. So we have full PIX support for variable rate shading. We shipped a version of PIX which supports this in the last update. This supports capturing variable rate shading, replaying it. You can inspect all the variable rate shading state. This is available for download on the PIX website. We're planning to do more here. We would like to build a visualizer to inspect the shading rates and let you look at a frame and see what shading rate was used for different tiles. You should look for that to come in a future update to PIX. But the basic tooling is there already, so you can start using this and debugging your shading rate usage. And then before we hand over to some partners to do some demos, I want to walk through a few other places to follow up. If you want to learn more about this technology, shortly after this talk in this same room this afternoon, my colleague Martin Fuller from the Microsoft Advanced Technology Group is going to be doing a second deep dive talk about variable rate shading. Now that we've kind of covered what the functionality of this is and shown some demos, he's going to dig into some more advanced techniques for how you might use this. So he's going to present some research we've been doing on, okay, you have this screen space shading rate image. Where should that come from? You maybe want to do some math on things like the previous frame to compute a good shading rate. And another thing he's been looking at is sparse lighting. Like, how would this technique integrate into a deferred shader? I strongly recommend checking out the Microsoft demo booth. That's over in the South Hall lobby, where we have variable rate shading running on an actual 4K monitor. We're going to show some demos here. But on this projector, looking at things and trying to assess, is that pixel quality really good? Zoomed in, it's kind of hard to see. So stop by there if you want to see it up close and in detail. This feature is shipping in the next version of Windows 10, which is codenamed 19H1. That's available today through the Windows Insider program. So you can get the SDK and an operating system that supports this now if you join the Windows Insider ring. And a couple of links to finish with. We've released the developer spec for variable rate shading on the URL below. This is a new thing for D3D. In the past, when we've built features, there's been a delay between us implementing a feature and the official API documentation showing up. And that documentation is kind of simplified and targeted more at higher level developers and maybe people who want a slightly simplified explanation. What we've done this time is we've just published the raw spec that we used while developing the feature and working with hardware partners. So that will answer kind of gory details about whatever questions you may have. And we have a sample showing how to use it at that URL. So I'm now going to hand over to some partners from Intel, Adam Lake and Kelly, who are going to show this in action running on Intel hardware.
Great. Thank you, Sean. All right. Hi, folks. Welcome. I'm Adam Lake. I'm here today with Kelly Gahn from Intel, and these lights are really bright. We work in the visual technologies team, and I'm going to give the Intel perspective on variable rate shading and the support upcoming in our Gen 11 graphics hardware. And Kelly's going to take a tour of some of the demo work that she's been doing in Unreal Engine. So, as I said, I want to give our perspective on why we think variable rate shading is important. And we have some ideas of where to use variable rate shading, so I want to talk through some of those examples. And then give a little bit of more information about our support for variable rate shading. Sean mentions the tierings and some of the optional features, so I want to talk you through where we are there. And then Kelly will do the demo. So what is this opportunity here? Just as Sean said, we observed this several years ago. There was a paper back in Graphics Hard around 2014 on coarse pixel shading. And at that time, we started thinking about this scaling issue related to display resolutions are scaling faster than we can put down transistor resources to take advantage of that. And so you want to think about how to optimally use your pixel shader resources on these increasing resolutions of displays. And this is important on integrated and discrete cards, but it's even more important on a 10 to 15 watt solution, and that's where our graphics parts play the biggest role. And so it's even more important to pay attention to using features like variable rate shading on integrated solutions. So in order to get this into the ecosystem, it really takes the entire pipeline working together collaboratively. So we have Intel investing in the hardware support, Microsoft working on API innovation and the operating system, and the application developers taking advantage of this feature. So we kind of have this cycle of feedback between us to explore the best uses of variable rate shading and to be able to take advantage of what we've invested in the hardware. So why do you want to use variable rate shading to solve this problem, the scaling problem? Well, the key thing is that you're able to control the shading rate independent of the render target resolution. So for example, using MSAA, you're still going to get all your depth buffer, stencil, and coverage masks. Those are going to be at sample rate, but you're going to be able to adjust the pixel shader throughput independently of that. And I show examples of a couple of pictures here, this barrel on the left and like this clothes hanger and cloth on the right, where we show on each of these the left and middle and right image. The leftmost image is the pure pixel shader. The middle is with VRS, and you can see the contrast difference. And then the upscaling technique, and Sean talked about things like dynamic resolution rendering, checkerboard rendering, and these are the kind of results you get in the upscaling image on the right. Now, we still advocate these upscaling solutions, and Intel has published open source implementations of these in DX12 last year. And these are software solutions that work on our hardware today. But what we're encouraging you to do is when you have hardware such as our Gen 11 graphics hardware, to go ahead and query for variable rate shading, and if it's there, to take advantage of it. So we have a couple of ideas of where we might use this, but we're still exploring these things, and we look forward to having conversations with our partners to take advantage of this feature. Up here in the upper right, we have this what we'll call level of detail sample. It's programmer R, just maybe a tech demo to flesh out some of our internal pipeline. And you can see there's 3 levels of detail in this. The red is shaded at 1 by 1, the green is 2 by 2, and the blue ones in the back are 4 by 4. It's obviously harder to see this here. Kelly will show some demos, and we have some work in our booth that you can go and see this up close. But using this idea of reducing the shading rate for things in the background is one of the opportunities I think it's useful to explore. Now, 4 by 4 might, on a small object, might have some visual artifacts, so be careful about that, but for demonstration purposes, the demo actually supports that. The other area we think this is going to be useful is when objects are blurred in the scene. And this could happen for a couple of reasons. One is the camera's moving, and so all the objects end up being blurry. The other is the objects in the scene are moving quickly through the scene. So you might already have motion blur happening in a post-processing pipeline. Well, it's useful to know areas that are already going to blur, there's no reason to render those with a higher resolution pixel shader. So we think this is something to look at using variable rate shading. And another one is whenever your objects have a slowly varying shading rate, and we have this cartoon Olaf model in the bottom right image where it's cartoon shaded, there's not a lot of change in the result, so it's not of a lot of value to shade that at a high resolution, so go ahead and reduce it there. Another scenario you could envision is a time when you're running low on battery. So you're in a coffee shop and your user is playing the game and they're trying to finish a battle with their friends, and you have 20% battery warning comes up. it might be an idea in your engine to say, hey, have a pop-up and say, hey, I can extend your battery life a little bit longer here if you're willing to take a lower shading rate. Would you like me to go ahead and do that? It's just one idea that I think is worth exploring. And then one of the things I wanted to share was when we were working on this Unreal POC, Kelly, myself, and a few others, we noticed that we had this idea, and it works pretty well. In fact, we sometimes thought it was hard to tell whether it was working or not, because the concept's very simple. You want to use VRS when you're moving in the scene, everything's moving around, but if you stop and somebody's there and they want to appreciate the beautiful vista because they got to the top of a mountain or wherever, these are scenarios happen where people are enjoying the visual quality and the camera's not moving, go ahead and do a full resolution render, and we call this relaxing the shading rate. This was something that seems to help mitigate any issues where someone might be trying to investigate the visual quality. Obviously this is an option that you could have turned on and off. So now I want to speak to Intel's implementation details on our Gen 11 graphics hardware that we will be launching this year. We support Tier 1. Sean talked about Tier 1 and Tier 2, so this is per draw call support. This is supported in hardware. The other thing is he mentioned these optional shading rates, and I've got this picture on the right-hand side of the slide. The variable rate shading rates in green, those are required core support. But Intel goes beyond those capabilities and supports the 2x4, 4x2, and 4x4 shading rates. So I encourage you, when you use our hardware, to query for those shading rates and take advantage of them. I mentioned a little bit of some speed up results we're seeing, and our partners that are doing application development are going to talk about the details of their work after Kelly's demo. And we will have some white papers and sample code of our own that will be made public this year, shortly after our hardware is released. Final thing here before I turn it over to Kelly, this is still early. We have a lot of exploration as a community with this feature, and I'm really excited about it, and I hope to see, we're going to work with partners and get this into games shipping on Intel Integrated Graphics. So thanks for your time. I'm going to turn it over to Kelly.
Awesome. Oh, hey, it works. Awesome. Alrighty, here. I'm going to play the man behind the curtain for a second. So, slides are wonderful and useful, but it's always nice to be able to see something in action. So what I'm showing you right now is that wonderful programmer art demo Adam was talking about earlier. This was basically us just trying to make sure this feature is working in our new hardware, which I have humming underneath me now. So essentially what we're getting out of this here is that you can see we're changing that shading rate in real time. The back, as he said, is in the blue, and you can see that those objects, as they move farther away, are choosing a different shading rate. Now, if I turn off the visibility, it becomes a trick of, okay, figure out where the artifacts are. It's a little bit harder to see on the screen, so I encourage you to check out both the Microsoft booth, and we have a demo in the Intel booth. So basically, this was a quick implementation to make sure that we have it working. We wanted to see what sort of scaling we could get out of this, so we made ourselves a little stress test. We made a really expensive pixel shader, essentially. And you can see that without variable rate shading, we're running slower, and we get around 2x performance when we turn that on. Benchmarks are fantastic for testing functionality and getting a theoretical idea of what's going to happen when you start implementing this feature. But at Intel, what we really care about is getting this in the hands of developers as soon as possible so we can learn from you and make sure that everyone gets to use all these features. So what we worked on is we branched Unreal Engine and made an integration there. That's what you're seeing here in this Sun Temple demo. So right now I'm running without variable rate shading on. And you can see, so essentially we're shading at a 1x1 pixel level. And then when I turn on VRS at a constant 2x2 level, you can see we get around like a 1.2x, 1.3x speed up, depends kind of on the workload. Again, here we're just enabling it across every draw in the scene, kind of a sledgehammer mode. But the really nice thing about it is that, again, we're maintaining the outlines of those forms really nicely. I can even go all the way up to 4x4, and here you're starting to see more of the artifacts, especially on hero assets like that medallion in the corner. And those are other cases that we're thinking about optimizing. You know, you could have your artists be able to tag those hero assets, detect the tag and say, hey, I always want to shade hero assets at a 1x1 rate, no matter how far they are from the camera. But really, the 2x2 is probably more representative of a solution that we would use in games. What's awesome, though, is we are getting 1.2x speed up and still maintaining a lot of visual fidelity. We also went ahead and implemented that a early version of that technique that Adam mentioned, which is the relax mode, essentially. So when you're not moving, turn off CPS. And then when you are moving, turn it on. So the faster you're moving, again, like that motion blur starts to kick in, you're not even going to notice that the shading rate has deteriorated behind you because you're spending your pixel shader resources where they're actually going to matter. So if you're, a sniper, when you're moving very little, you want it to be really high fidelity. You can see every pixel with really high granularity. But when you're running around, you want to be able to run around with really great performance. So kind of an intro to how an FPS might model experiment VRS. We look forward to hearing from you guys on your feedback on what you'd like to see from this implementation and how you would think about using this in games. So thank you very much.
All right, so my name is John Kletzley. I'm a graphics engineer at Firaxis Games. I've been there for quite a while. I'm here to talk about some experimental VRS work we did in the Civilization 6 engine. If you're not familiar with Civilization, it's a strategy game that's about building an empire through time. We originally shipped Civilization 6 in October 2016, and the most recent expansion, Gathering Storm, just shipped in February. So this is a typical screenshot from Civilization. If you've played strategy games, you probably play games that have this kind of a view. As you can see, there's a lot of detail here, and it's really important for us to preserve detail. So all of our rendering technology is based around preserving detail, anti-aliasing, and clarity. We are predominantly forward-rendered engine, and all the screenshots today were taken with 4x MSAA. And for the next few slides here, we're just going to zoom in on this one little area of the screen so that we can investigate the quality of shading rate. So if we look in here, we can see there's essentially two classes of objects on the screen. For a strategy game like Civilization. We have the environment, terrain, water, and then we have a whole bunch of tiny stuff. Vehicles, buildings, even user interface elements like that culture border icon you see in the lower right. And what we find is when we run the game at high resolution like 4K, all the tiny stuff looks great. The detail is preserved. You get increased clarity. Actually, I think running at high resolutions for games like strategy games that have a lot of detail is actually a very compelling case. But we find that the environment just starts to get too expensive. It's just a lot of pixels to fill for that environment. And most of the time, the environment doesn't actually have detail that is contributing to the experience. So the first experimental VRS mode that we integrated into the engine was based off of a tier 1 functionality. And the idea here is we're going to use the 1x1 shading rate on tiny objects. We're just going to leave them alone because they're actually providing value to the scene. And we're just going to blanket turn the shading rate down to 2x2 on all the environment. So the terrain, the water, we're just going to turn the shading rate down. This also fits into the fact that, as Sean mentioned, tiny triangles and turning the shading rate down further is not a great fit. So this sort of fits with the strengths of VRS as well. I should note everything else, post-processing passes, anything that we've deferred, user interface is of course still going to run full rate. However, we do notice that there are some artifacts here because the environment does have some detail in it, right? And if we just naively turn down the shading rate without then compensating with some sort of a filtering, we end up with what we can see the coarse pixel boundaries here, and we just kind of end up with a pixely look, which really isn't great. And this is especially visible in high contrast regions in the environment, like the shadow of that building or that user interface element, which is actually rendered in the environment shader. So we developed this idea of having a multi-resolution resolve of our 4x MSA, where we're able to separate out the samples that were rendered at 2x2 rate, and then we can filter them and composite them back together. And if we do that, we end up with, I'll go back and forth here, we end up being able to filter the 2x2 samples so we get a smooth result and combine that back together. And if you notice, I'll go back one more time, the buildings still retain full quality. And this is going to have correct per sample coverage. So it's sort of an advancement over if you just rendered some objects at a half rate render target. So the results here were we were able to retain all the detail on tiny objects. The environment got a little bit of blurring. It was only visible where there was detail. And the performance is pretty significant uplift. For this particular scene, running on an NVIDIA 2060 at 4K, we got almost a 17% reduction in the time required to render the frame. And for this scene, that took us from below 60 frames a second, like middle 50s, up above 60 frames a second. So it is relevant performance. We also decided, because we have a strategy game that's very open-ended, we didn't want to just test one scene. So I also ran our Gathering Storm integrated benchmark, which is sort of an extreme case where the number of tiny objects is extremely high and the amount of environment that's visible is about the least you could expect to reasonably come across in the game. And we still got 8.2% reduction in time to render the frame. And that's an average across the whole benchmark. So the second mode that we did is based off of tier 2 functionality. The idea here is to build on what we learned from our tier 1 work for hardware that might support tier 2, and to go slightly further and to sort of pull some detail back into the environment using the image-based shading rate option. So what we did is we just looked at the results from last frame for the opaque pass, and we ran an edge detection filter on luminance, and then we selected regions that had some sort of edge in them to run the environment back at full rate. Now remember, we're still running the tiny objects at full rate everywhere. So this is the result when we do that. Here you can see an overlay of the blocks, sort of encoded in red. Highlight here are the areas that where it detected that there were edges that needed full detail preserved. And the blue is where it said, no, you can run that at a lower rate. And the results here were very good. We were very happy with the quality. The one exception with the quality was if you have something like an extreme hot specular highlight on an animating normal, like in the ocean water. I'll talk about this in the future work section, but that was the one exception. But we feel like using edge detection like this is probably like a 90% solution that gets you a lot of value pretty easily. And we were able to preserve most of the speed up that we got. So in this particular scene, we were still getting 12.7% reduction in time to render the frame. And across that sort of a worst case benchmark, we were getting a little below 7%. So here you can see side by side the reduced shading using the tier 2 image-based shading rate and on the left and full rate on the right. And if you look closely, you can see some quality differences, like in the shadows in the water, a little bit less detail on some of the terrain that's showing through the water, but it's pretty good quality. If you're running this at 4K, you're probably not going to notice those small differences. So future work. I said that we ran an edge detection filter, but right now our edge detection filter can pick up edges from things that were rendered at 1:1 rate because we're not separating those samples out. So separating those samples out in order to reduce false positives would be one way that we can improve this implementation. And we also have the idea of selecting the shading rate based off of game content. One case I mentioned was you have this, I took a screenshot here of the ocean with the sun reflecting right off of it. You really want this rendered at full rate. It's pretty important for, the look of our game is all about stuff reflecting off of the terrain, so this is an important case. So here you probably will want some way of detecting you were anywhere near that specular highlight and ensuring that you ran at full rate in that area. But still, around the edges there's plenty of areas where you can reduce the shading rate and get savings. As a strategy game, we also have tons of user interface, and our user interface artists really love making semi-transparent user interface, which is a little bit painful sometimes. But this now gives us an opportunity. We can reduce shading rate behind large semi-transparent panels, user interface, or all sorts of different game-specific ways that you can now tune your performance to help reduce shading costs. My experience with using the actual API was actually quite pleasant. This is obviously Civilization 6 is not a new game. It wasn't designed with VRS in mind, but I was able to integrate this in very quickly and iterate on a couple of ideas and try out where VRS might be able to help make strategy games work better at high resolutions. I updated the D3D COM interfaces to the latest in order to get the feature working, but all of the work that I did here was done without updating toolchain. So there are some parts of the VRS spec that require you to use the new compiler, a D3D compiler, or the new shading model. Those weren't really an option for me in the time frame involved here, but we were still able to do all of this work with only using the COM interfaces. So there's even more you could do if you were to use those additional features. And there were, I will say, minimal shader changes to the game required. If you had asked me before I started this how many places where we were depending on consistent gradients or depending on resolution matching the gradients, I would have said there were no places. There were a few places, but I was able to find them and fix them fairly quickly once I started working with the API. But honestly, the thing that's most exciting for me about VRS is that it really gives you the ability to sort of tune things with very little effort into sort of an existing rendering pipeline. So it's a very low friction way to get value added into your game. So I think this is just the beginning. There's lots of ideas of how you can drive shading rate. And we saw some ideas presented earlier, and this is the stuff that I've come up with, but I think there's a lot left to look at. I just want to quickly, it's a little bit difficult to do demoing at 4K. I'll see if I can wake this up. It's a little bit difficult to do demo at 4K. This projecting system doesn't support 4K. Oh, the screen isn't showing up here. Seven. Anyway, so if you're interested in, oh, that's not me. If you're interested in getting a good evaluation of the performance and quality trade-offs, I would encourage you to go to Microsoft's booth and play with the demo yourself there. Like it's, I think, much more compelling there. But we wanted to be able to show something here. So for those of you who aren't able to make it to the expo, I can just give you this is what it looks like for especially the shading rate image for tier 2 selection. Well, in a minute, but maybe we want to do you want to finish up and then we can go back to this?
So yeah, any questions for any one of the presenters from today? We have a mic in the middle. If you could use that, that would be great for the recording.
So some of those hardware vendors, like some vendors have a call option as well. In addition to the one by one, 2 by 1, there's actually a call ability to call whole tiles. What was there a reason for excluding that from the DirectX spec, or?
We did not include a call option, basically because we felt that was pretty redundant with the functionality of stencil buffers.
Interesting. Okay, thank you.
Thank you for the nice feature into API. And I have 2 questions. First, what kind of upsampling filter are you using? It's interpolation or box filtering, because the artifact which I observe in the presentation is blocks, so it's no interpolation.
Yes,
or
the hardware upsampling is just replication. The same pixel shader output is replicated to each frame buffer. One of the things that John talked about is for the implication in Civ 6, he actually did his own filtering as a post-process to improve image quality, which was...
So it's possible to emulate some in the interpolation after using some quads shading features, because it's not good in appearance, the block structure.
I mean, yes, it is up to us to implement the features that we want, but I mean, you're going to want different things in different contexts, so I think that that's actually reasonable.
Okay, and the next question, is it possible to control shading rate for every textures, not only for calculation? For example, a lot of things game developers do using multiple render target, render in different resolution. For example, for water, it can be underwater surface in low resolution, reflection in another resolution, some particles. So a lot of different texture fetch in different resolution are separated by different render passes. Is it possible to control shading rate for the textures independently?
So are you talking about textures that are in different render passes?
No, to combine all things in one render pass, but use the different rate for every texture fetching.
Not within a single pass, no.
Because
you can do
maybe I've
bias,
seen the NVIDIA solution, and so they control. Maybe I'm wrong.
This shading rate control is per dispatch. It's not within the shading.
Now it's for the same shading rates for the text cells and
yes, that's
for
correct.
all. Okay, thank you.
So for one of the examples, you had the triangle shaded with multiple different rates. So is that supported, first of all? So having a single object with multiple rates?
Yes, so that sample would be done using the screen space image.
Okay.
To set the shading rate per tile. I actually, to those of you who are paying attention, there's a slight cheat on that slide. The graphics I showed is actually not possible with the VRS API. And the reason for that is that when you control the shading rate via the screen space image, that's a tiled format. I talked about the tile size being 8 by 8 up to 32 by 32. The screenshot I showed was actually using a 2 by 2 tile size, which is not a thing you can really do, but it's easier to fit on a slide without it being fiddly and small.
Sure. And then, so with LODing, is there a solution for like dithering between the different rates, just to avoid that pop-in of the shading?
That's a great question. Not directly. You probably, and particularly that kind of thing would play really well with temporal anti-aliasing techniques. I can imagine a temporal dithering, which would then be fixed by the temporal post-process. In Martin's next talk, he's going to talk a little bit about some things that tie into that kind of thinking.
Hi, thanks for the really good talk. I was wondering when, specifically on exactly what you're doing right now, which is scrolling in Civilization, since you're using the previous frame's output to feed into the next frame's image-based multi-resolution, do you just use it as is, or do you try to do the same scrolling as you did in the game?
We don't do any reprojection for this demo. That might be a way to improve the quality, but to be honest, one of the times when it is safe to reduce shading rate is when you have motion in the screen because you can't see that the shading rate is lower. So this is not an integration over time. This is one frame delay. So if you're running really fast, you're just not going to notice that you're one frame behind. So what we found is the quality here is good enough. I wouldn't want to add any cost by doing any sort of reprojection with what we've seen.
That makes sense.
There are cases where you might want to, but for us, it seems like it works really well without it.
Good for you. What is the approximate, like when I saw all the motion, not motion detection, but yeah, edge detection cost, and then objects, like writing small objects into the texture, I'm like, that sounds really expensive to do every frame. I'm glad that you are able to still get perf speedups, but do you have any numbers on how much time per frame, like the percentage that you're spending on VRS image generation compared to actual color generation?
On image generation? Oh.
Yeah, like what's the overhead?
I don't have a number off the top of my head. When I was doing most of this work, I didn't actually have access to the profiling tools, so I was sort of flying blind. But we were able to get pretty good speed up, so it's not that expensive.
Cool. Thanks a lot for everything, and Civ 6 too.
Performance improvements also included the overhead.
Yes, all the performance improvements that we mentioned included the overhead of the post-processing or the custom resolve pass for tier 1 and the generating the shading rate for tier 2. So,
yeah, just have a question about you mentioned you have the per triangle control on the shading rate. I wonder, does it work with the tessellation shader?
Yes, absolutely. That will work with any shader stage. Well,
cool.
the shading rate is written by the vertex or geometry shader, but that will play nice if there's tessellation as well.
Yeah, thank you.
Hi, thanks for the nice talk. I was curious if we are kind of capped by 25% increase of this feature. So, every number that we saw in the demo was kept like by 25 factor increase, but you're decreasing resolution 4 times. So it's kind of under of should be expected from half resolution rendering, for example. Is there like an upper limit of like for efficiency?
That's going to be very workload dependent. So that
what's the base
it would be easy to construct an artificial benchmark where it would be completely linear with shading rate, but that would be something that was just completely bound by pixel shading. With a real workload, we've been more interested in testing perf on somewhat realistic workloads in an engine where there's expensive geometry processing and post and other kinds of things.
So
the numbers we're showing here are kind of realistic.
I can speak to our demo. Like, we are only cutting the shading rate on the main opaque pass for the environment. So there's a lot of work that's not included in that. And the tiny objects are very expensive. It's just that VRS isn't the right tool to try and speed those up.
Yeah, understood. Thank you. But the question I wanted to ask, if I run like a best case example, like full screen quad, should I expect like 4-fold increased?
If you were completely pixel shader bound, yes.
Okay, thank you. And another thing I was curious about, that's about the cost of the switching shading rate, like CPU or GPU flashes. Like, is that a chip command to like switch shading rate, like per draw primitive?
The per primitive shading rate is reasonably cheap to switch. I mean, it's like any pipeline state. You probably don't, you will probably want to sort by it. It's going to be less expensive than something like changing PSO.
Okay.
Setting the screen space image is fairly expensive, so that's something you would want to do once per frame rather than repeatedly changing it.
Okay, so it's not very suitable for example, sorted particles or something like that. It should be expensive.
I didn't follow that.
If you're like sorting, for example, you take a bunch of particles sorted like in back to front order to render with blend, and then you want to switch the shading rate for different like particles effects. You should doing a lot of switches.
I would assume in that case you probably have like clusters of them that you want to do, or maybe just have the shading the same for all of the products.
Okay.
And that would work fine. But if you wanted to try to change it, vary it for each one of those, you might incur some performance.
Yeah, and that would be the CPU or GPU cost?
GPU cost.
And how much?
On Gen 11 hardware, I mean, I'll just, I don't know if I can speak specifically to the numbers right now, but I'll say like it'll be under 1,000 watts. You can figure out that, but should be under 1,000 watts.
Okay, is it for Intel GPUs, right?
Yeah.
Okay, thank you.
One thing I should just call out on that is, from our thinking about VRS, particle systems are actually one of the premier use cases for this. It's incredibly rare that a particle system needs high shading rate. This is something where dropping all the way to like 4x4 is probably fine. So if there's one quick and dirty thing and you don't want to spend any time at all adopting VRS, I think a reasonable thing would just be set the coarsest shading rate you can around your particle pass and don't do a single other thing in the game, and you'll get a perf win for all those big clouds of smoke, and it will look indistinguishably different.
On a somewhat related note, did you try it with depth renders? Or does the overhead dominate the pixel costs if you're doing, like, say, shadows?
Martin's talk that's coming up is going to go into a bit of that kind of thinking. We have a couple of minutes left. Do you want to walk through some of the demo now that it's up?
Well, this basically is the demo here. I kind of panned around while we were doing questions a little bit. I don't know what these spikes are, but they're not my fault. This is not running at 4K, and it's actually running on faster hardware than what I tested on, so the frame rates here are just super, super high. Sort of barely GPU limited here. But you get an idea of the shading rate image being generated based off of data from last frame. You'll notice occasionally you'll find things that are flickering. Really, let's see if we can find a spot where it's doing that. All right, so this is flickering here. You just can't see it. Like, go to the expo and look at Microsoft's booth and run a demo yourself. The quality is not going to be apparent from this, so I would encourage you to do that to get a better idea of how close the quality was. At one point, I was reviewing some of the marketing materials, and I was convinced that they hadn't turned it on properly when they took the screenshots. I was wrong. It was working properly, so it's pretty good.